In the previous lecture, we have studied about the charging of a capacitor in CR circuit, and we learn about how capacitor is charged and what is the value of charge at any given time instant. Also, we calculated the potential energy, electrical potential energy conserved in the capacitor, and we also calculated the current at any time in the circuit. Here we will now study about the discharging of a capacitor. So let's start. In this case, cell is removed from the circuit and the capacitor itself behaves like a cell which supplies the current to the load resistance. Here it is shown the diagram of a discharging of a capacitor. This is a capacitor which now behaves like a cell. This is positive terminal, this is negative terminal, and this is the load resistance R, that is external resistance R. Now applying Kirchhoff's law in this, so minus IR plus Q by C equals to 0. This implies minus or minus dq by dt into R, because in this case charging in charge is decreasing, so we have taken minus dq by dt. So this implies minus or minus dq by dt into R plus q by c equals to 0. Since I equal to minus dq by dt, a charge is decreasing, or R dq by dt plus q by c equal to 0. This implies dq by dt equals to minus q by rc. This implies dq by q equals to minus dt by rc. This implies integration q naught to q dq by q, because our initial charge is q naught and final charge becomes at any time q, minus r by 1 by rc 0 to t dt, and after integrating log q naught to q limiting value minus 1 by rc into t, or log q by q naught equals to minus 1 by rc into t, or q by q naught equals to e to the power minus t by rc. This implies q equals to q naught into e to the power minus t by tau. So here finally we have got the value of q at any time given by this formula, q equals to q naught into e to the power minus t by tau. It is also exponential function, and tau is as we know, tau represent rc and called capacitive time constant, where tau equal to rc equals to called capacitive time constant. Now at t equal to tau, that is when time is equal to the capacitive time constant, q becomes q equals to q naught e to the power minus 1 equal to q naught by e, or equals to 0.368 q naught. That is, in this time interval the charge on the capacitor remains of this value of initial value, that is 0.368 of q naught. Here it is shown in the figure. Initially it is a maximum charge on the capacitor, and now due to discharging, charge is removing from the and decreasing on the capacitor, and a time reach when t equals to capacitive time constant, the value remains 0.368 of q naught. Thus capacitive time constant, now can we define capacitive time constant in the discharging case. Thus capacitive time constant is the time in which charge becomes 1 by e, that is 0.368 times of its initial value during discharging. This is a capacitive time constant during discharging, and we have defined it here. Now discharging current, it is given by I equals to minus dq by dt equals to minus d by dt, putting value of q here, q naught e to the power minus t by tau. Now q naught is constant, so it comes out of the differentiation, minus q naught d by dt to the power minus t by tau. Now differentiation of this will be minus q naught into minus 1 by tau, because difference, so constant will be multiplied, minus 1 by tau into e to the power minus t by tau equals to c, and q naught is equal to c into 1 by rc e to the power minus t by tau. C will cancel out, or I equals to e by r e to the power minus t by tau, or I equals to I naught, that is initial current, e to the power minus t by tau, where I naught or I zero is equal to E by R, and this is the initial value of current in the circuit, and the direction of current is opposite the direction of charging current. Here it is to keep in mind that direction of current is opposite to the direction of charging current. Next, the current on the graph is shown here. This is the initially it is I naught, which value is E by R, and after time constant, capacitive time constant t equal to tau, in the case of discharging it becomes 0.368 of I naught, and next, the value of potential difference across the resistance is given by VR equals to IR. This is the potential difference across resistance R, or I naught R into e to the power minus t by tau, or I naught is equal to E by R, e to the power t by RC. R cancel, so we have potential difference across resistor is e at any time e to the power e into e to the power minus t by RC. Again, the value of potential difference across the plate of the capacitor is given by Vc equal to Q by. This is the potential difference across capacitor, Q by C. We know that this is the formula for potential difference across the plate of capacitor, is equal to Q naught by C e to the power minus t by RC equals to, now putting value of Q naught is C by C to the power minus t by RC, or Vc equals to E into e to the power minus t by RC. So this is the value of potential difference at any time across the plate of capacitor. Next, the heat released through resistance R is given by dH equal to I square R dt, or H equals to integration ds, integration t1 to t2 R to I naught, putting the value of I. So R square I naught, R into I naught square e to the power minus 2t by RC into dt, or H equals to R into E square, R and R will cut, I naught, putting the value of I naught. So R into E square by R square, okay, T2, and T1 to T to the power minus 2t by RC into dt. Now E square by R into, taking integration, will be 1 by the constant value will be divided minus 2 by RC, and integration of e to the power 2t by RC is e to the power minus 2t by RC, and T1 to T2. So the heat generated during full discharging, H equals to 0 to infinity. Our initial time is T1 and final time is T2. The initial time is 0 and final time is infinity. And that is full discharging, when capacitor becomes discharged, 0 to infinity R I naught square R into I naught square e to the power minus 2t by RC dt, or R into E square by R square, 0 to infinity e to the power minus 2t by RC into dt. Now E square by R square into 1 by minus 1 by 2 by RC e to the power 2t by RC 0 to infinity. e square by r, so true, or minus 1 by 2, this minus 1 by 2 into e square by r into rc, rc equal to taking limit, this will when we put infinity, this will be 0, and put 0, this will be minus 1. So solving, r will cancel, so 1 by 2 c square, we are left with 1 by 2 c r. It is here shown the final value of heat generated during full discharging, 1 by 2 c square. Next, the value of energy stored in the capacitor at any time instant is given by UC equal to 1 by 2 C into Vc square. In energy stored in the capacitor at any time, we know the formula for potential energy is 1 by 2 C Vc square. So 1 by 2 C into, now the value of Vc is E into e to the power minus t by rc to the whole square, 1 by 2 c square e to the power minus 2t by rc, or uc equals to 1 by 2 c e square into e to the power minus 2t by rc. So this is the value in capacitor at any time interval t, energy stored, that is electrical energy stored. Now in elementary form we can write duc equal to 1 by 2 c into 2 Vc into dVc, because C remains constant, one potential difference is changing, so we have differentiated potential difference. So 1 by 2 C into 2 Vc into dVc, or C Vc into dVc, or using the value of Vc, so C into e to the power minus t by tau, and differentiation of Vc will give e to the power into minus 1 by tau into e to the power minus t by tau dt, or duc equals to minus ce square by tau into e to the power minus 2t by tau into dt, or minus ce square tau equals to rc, putting the value of tau equal to rc, and e to the power minus 2 into t by tau into dt. So duc equals to cc cancel, duc equals to minus of e square by r e to the power minus 2 into t by tau dt. Hence the rate of energy change in capacitor is given by duc by dt equal to minus of e square by r e to the power minus 2 into t by tau. This is the value of energy change in capacitor, rate of energy change in capacitor, given by this value. Negative sign indicates that the energy in the capacitor is decreasing. Negative sign only represent that value is decreasing, and if we take modulus value, then we have to remove the negative sign. So this is our case of discharging in the capacitor. Now let's see some problem. A capacitor of capacitance 100 microfarad is charged by connecting it to a battery of EMF 12 volt and internal resistance 2 ohm. A. Find the time constant of the circuit. B. Find the time taken before 99% of the maximum charge is stored on the capacitor. We know that time constant is given that tau equal to CR, 100 microfarad into 2 ohm equal to 2 microsecond, solving it, 200 microsecond, these microfarad and ohm, microfarad into ohm will be second. The charge at time t is q equal to c into, this is the formula for charge at any time t, so c into 1 minus e to the power minus t by rc, or q naught into 1 minus e to the power minus t by rc. Now given, when find the time constant of circuit, B, find the time taken before 95% of maximum charge is stored on the capacitor. 95%. So 95%. So we have Q equal to Q naught into 0.99%. So hence putting the value of Q in this formula. So Q naught into 0.99 into Q naught into 1 minus. Here we have value given Q equal to Q naught, that is charge on a capacitor at any time. Q naught is 0.99. So hence Q naught into 0.99 into Q naught into 1 minus e to the power t by 200 using the value of that time constant, or 0.99 equals to 1 minus e to the power minus t by 200, or e to the power minus t by 200 equals to 1 minus 0.99 or 0.01, and taking log e to the power minus t by 200 equals to log 0.01 or minus t by 200 equals to this value, or t equals to minus 200 log 0.001. Taking magnitude of t equal to 200 to log 0.01 equal to equivalent to 0.92 milliseconds. Solving it, putting the value of log 0.01 and multiplying with 200, we get this value, and this becomes 0.92 millisecond. Next question. The plate of a microfarad capacitor charged to 400 microcoulomb are connected through a resistance of 1 kilo ohm. Find the charge remaining on the capacitor 1 second after the connection is made. The time constant is tau equal to CR equal to 50 microfarad into 1 kilo ohm equal to 50 into 10 to the power 50 millisecond. Fifteen to 10 to the power 3. 15 to solving it, 15 to 10 to the power 3 second equal to 50 millisecond, and t equal to 1 second t by CR equals to 1 by 15 to 10 to the power 3 second, or equals to 1000 by 50 equal to 20. The charge on the capacitor is Q equal to Q naught e to the power t by RC. So putting the value, we have 400 microcoulomb into e to the power minus 20, 400 microcoulomb by e to the power 20 equivalent to 8.2 into 10 to the power minus 7 microcoulomb. Answer. Next question. Find the current I supplied by the battery in the network shown the figure in a steady state. B, find the charge on the capacitor. Here the network is shown. This is our capacitor, this is our battery, and these are resistance. So we have to find the charge. We have to find the current supplied by the battery in the network on the figure, and B, find the charge on the. In a steady state capacitor offers infinite resistance, so above circuit reduces to, and because this offers infinite resistance, so no current will flow through this, and this is useless. So our circuit will reduce like this. So in this case, I will be, hence I equals to 2 EMF divided by 2 plus 6 EMF by resistance, total resistance 2 by 8 equal to 1 by 4 ampere. As no current is flowing through middle circuit, so PD across capacitor equals to PD across 6 ohm resistance, in this ohm resistance. So we have 6 into 1 by 4 or 3 by 2, 1.5 volt. So potential difference across 2 microfarad capacitor is 1.5 volt. Here it is, as no current is flowing through middle circuit, so PD across capacitor, PD across 6 ohm resistance, 6 into 1 by 4, 3 by 2 into 1.5 volt. So charge on capacitor Q equal to CV 2 microfarad into 1.5 volt equal to 2 microcoulomb. Answer.